Well, today we're going to talk about what happens when we apply a reverse voltage to a PN junction. Last time we spent time looking at a zero bias junction where they're at thermal equilibrium, and we looked at how the conduction band and the valence band bend through the space charge region, and how we have a built-in voltage that is between the conduction energy and on the N side and the conduction energy on the P side. And also we looked at the work functions between the Fermi energy and the intrinsic Fermi energy on both sides. And we found the space charge width as well as the electric field in the space charge region. So we spent a lot of time kind of looking at that. And now what we're going to do is look at what happens when we add voltage. We're not going to add voltage in the forward direction. We're actually going to add it in the reverse direction, what we call the reverse direction. And when we do that, we're going to take our PN junction with the electric field in it, and we're going to apply a voltage, and when we do that, the junction won't be at thermal equilibrium anymore. So once that happens, then we don't worry about things being constant, the Fermi energy being the same or anything like that. The Fermi energy can be different if there is some kind of energy coming in and causing it to be different. So it won't be constant. A voltage is applied, VR, and VR is applied such that the positive end is connected to the N and the negative is connected to the P. And when we do that, the Fermi level actually ends up getting pushed down on the N side. When that happens, the depletion region or the space charge region gets bigger because the voltage that's being applied is actually enhancing the electric field. So it's making the electric field stronger. When it makes the electric field stronger, it even more prevents current from flowing. So the Fermi level on the N side is lower than the Fermi level on the P side, and we will soon look at a kind of a diagram and how that looks. And as you can see, the Fermi energy stretches down a little further now on the N side than on the P side, and the boundary that the electrons have to cross to be able to flow through the space charge region is now increased because of the voltage that's been applied across that junction. So what we have now is the built-in voltage plus whatever reverse voltage we actually end up applying. So when you end up with that, you can calculate the space charge width and the maximum electric field, but you just add the reverse voltage to the built-in voltage. So now that you had an equation to find all those distances, all you're going to do is modify it slightly so that we reflect the fact that the reverse voltage is now enhancing the built-in voltage. The magnitude of the electric field in the depletion region also increases, and it's still at its maximum at the metallurgical junction, but since the widths have changed, the electric field is going to change also. So if we look at our old information that we had about electric fields in general, we see that we have the graph that we made in the last class about where the maximum electric field exists. Remember, it's negative because negative electric field is calculated bound, but we remove that when we're dealing with the electric field most of the time. We usually just find its magnitude and we don't worry about the negative side. But at that point, at the maximum point, the relationship between the doping concentration and the width of the depletion regions causes those two to be equal at that point. So we can use that and actually we can get that and combine either one of those equations because they're the same. And we can combine it with the distance equation, and what we'll end up with is a maximum electric field equation that, again, just incorporates the reverse voltage in the equation that we were already using. We can also, and this is something that we did not do before, but can be done with the maximum electric field equation, it can actually be reduced to this much simpler form, which you can use if you know the width of the depletion region. If you don't know the width of the depletion region, then you're going to have to calculate that whole thing anyway. But if you do happen to know that, then it's going to be a lot easier to just use that alternate form. You can use that with our original electric field equation as well. If you just have the built-in voltage, you can use -2 the BI over W and get that value. It just happens that if you haven't calculated the width and you don't need to, then you might as well use the other equation. But if you've already calculated it, it's going to be easier to calculate it when you use that value. So the other thing that happens when we have the depletion region and we have separated charges, anytime you have separated charges, you're going to have capacitance. And there is a capacitance across the PN junction, and the value of the capacitance per unit area just depends on the doping concentrations and the voltage. And I'm not going to go through and derive all that because it looks really pretty similar to what we've seen before with junction equations. It has a mixture of doping concentrations on the P side and the N side, and we have incorporated the reverse voltage as well as the built-in voltage. And we can also get that, again, if we know the width, we can just take the permittivity of the semiconductor and divide it by the width, and that will give us the value of the capacitance per unit area. This is not the actual capacitance. The actual capacitance is only known if we know the cross-sectional area of the device. Oftentimes we don't. But if we do, then we can calculate the actual capacitance versus the capacitance per unit area. So that's one topic. I'm going to jump to another topic. So don't get completely lost because this is beneficial to the next thing we talk about. But I'm going to talk about one-sided junctions. One-sided junctions are just basically, they're more of a model than anything, but it's basically a model of what it would be like if we doped one side of the material much, much, much heavier than the other. So on this, we've got the P material is really heavily doped. You notice the doping concentration is way down there in the negative, and it's got a very, very narrow depletion region because, of course, the heavier the doping concentration, the narrower the depletion region. This is actually a situation in which the number of acceptors is a lot greater than the number of donors. So we call this a P plus N junction. And in this case, the width of the space charge region really pretty much only depends on the doping on the N side. So we can use a similar width equation, but it's actually a little simpler because it's just approximately equal to the equation we use to find the width just on the N side. Again, you'll notice that the reverse voltage is incorporated into this width equation, and that is something that we can use, and if we didn't happen to have one, we could also not have that in there. But we can also find the junction capacitance per unit area in that one side by just taking the junction capacitance equation and modifying it slightly to just reflect what's going on the N side. This is actually going to become applicable when we start talking about metal semiconductor junctions, when we have actually doping on one side, but then we have actually a metal, and that interaction creates the depletion regions that we need and such and so forth. So we actually only have one side of a semiconductor, so the one-sided junction is used as a model to express the equations we're going to need to use. So also remember that what I was just talking about, the P side was more heavily doped, and if we can also do the same thing with the N side, we could dope that more heavily, and then the material would be PN plus, and in transistors you can even have something like NP plus, N plus plus in an NPN semiconductor device if you wanted to. So you can actually dope even farther than that. But the last topic that I'm going to talk about is breakdown in junctions. And this again is a little bit different topic, but not terribly different. But when we apply a reverse voltage to a PN junction, we can only apply so much. We can't apply an infinite amount of voltage. The maximum amount we can apply is called the breakdown voltage. And when that happens, a lot of current suddenly starts flowing through the junction. And of course, that can be a problem depending on if the junction is designed to do that or not. So there's two mechanisms that are in use when we're talking about breakdown. The first one is what we call Zener Breakdown. And that happens if you have a highly doped junction and then basically the junction is so narrow between the two because you've got heavily doped material on the N side and heavily doped material on the P side. And the conduction and valence bands are so close that electrons can actually tunnel through to the P side. And we'll talk about that in a minute. The other thing that can happen is something known as avalanche breakdown. And that happens when you have minority electrons and they gain enough energy to kind of go into the space charge region and crash into other atoms and create electron hole pairs. And what ends up happening sometimes, not always, sometimes this can be controlled and made use of, and sometimes it creates a runaway process in which more and more carriers are created and the current increases more and more and then the diode burns up. But that doesn't always happen. There are diodes that are designed to use this type of breakdown mechanism and still work properly. So the first thing I'm going to talk about is Zener Breakdown. Zener Breakdown is caused basically with using tunneling, which we talked about briefly and we're not going to go back and talk about again. But you can see that the conduction band on the P side and the conduction band on the N side are really, really far apart. And the Fermi energies are really far apart. And because of that, the distance between the conduction and the valence band in the middle of the space charge region is actually really narrow. And because that occurs, what can happen is the electric field becomes so strong that it can actually pull electrons from the valence band into the conduction band. So you get this strong electric field and electrons migrate over to the other side. And then once there are carriers, there's reverse current and that starts flowing through and basically creates a current through the depletion region and actually causes current to flow readily. A diode that is designed this way doesn't get damaged. It's designed to be working in that particular way, so we don't worry about it being damaged in any way. The Zener breakdown phenomena is only used with some Zener diodes, though. Only diodes that are less than about 4 volts for Zener diodes actually use this mechanism. The other mechanism that's used, the avalanche breakdown, is actually used for some Zener diodes, but they're all called Zener diodes even though they don't all use Zener breakdown. So the other way that the reverse voltage can break down is if you have the space charge region, and in the P region you will have minority carrier electrons, and in the N region there are holes. And this happens with both types of minority carriers, but I'm only going to talk about the electrons, just to let you get the idea. but there are a couple minority carrier electrons, and they just get enough kinetic energy, basically. They just have enough energy due to the applied voltage, and they start going into the space charge reading and hitting other electrons and striking them from their bonds and creating electron hole pairs inside the space charge region. And of course, the space charge region isn't supposed to have any carriers. So once there are carriers there, they start to move, and the electric field causes a current to go because there are now carriers in the space charge region. And those carriers continue to hit other carriers if that's not moderated in some way. You can actually have continued collisions that cause so many electron hole pairs that the current can't be stopped. But this can also actually be something that is designed. Most of the time in most PN junctions, the avalanche effect will be the one that predominates. And sometimes avalanche breakdown leads to the diode burning up. But if we want to design a diode, we kind of need to know what the breakdown voltage should be, or how to design a diode even to have a particular breakdown voltage. So what we do is we model the junction as being one-sided, because it really almost is. So basically that's how we model what the breakdown voltage would be. And when we do that, the breakdown voltage actually depends on something called the critical electric field, which is really the maximum electric field. So it's the maximum electric field that is occurring when that breakdown voltage is happening. And we will talk in a minute about the impossibility of actually finding that number. N sub B is just the doping concentration on the low side of the junction. So that part is something we can find and something we can determine. And of course, the permittivity of the semiconductor and the charge on the electron we already know. But the basic problem with this method is we really can't find that critical electric field very easily. So what is often done is we use graphs when we want to model or design one of these junctions. And this is a graph that basically relates the critical field to the doping concentration on the low doped side. So this is something that, and you'll notice that there's an area of it where the avalanche effect is taking place, and then there's an area where there's tunneling or the Zener effect. So you'll notice that does depend on doping concentration. You need really high doping concentration in order to have a Zener junction. So the other thing that is used is a graph that basically takes the breakdown voltage and relates it to the impurity concentration, which was on the previous graph. So really, you can go through and just use two graphs and come up with a design relatively easily. So we're going to do an example, and when we do that, we're going to actually make use of the graphs that we have. So we're going to start out, and we want to design a silicon PN junction, and we have the temperature at 300K because we always have the temperature at 300K now. And we have a donor concentration of 3 times 10 to the 8th. And we want to design an ideal one-sided N plus P junction diode such that the breakdown voltage is 100 volts. And right from the beginning, we're going to say that we're not going to get this exactly right because we're using graphs. And graphs are not perfect by any means. But where we start is what we want. So what we want is the breakdown voltage. And the breakdown voltage is 100. So we're going to go across and we're going to intersect with the line that is marked silicon. And it is in the area of the graph that says one-sided abrupt junction, which is what we're doing. And at that point, then we follow the line up, and that gives us our doping concentration on the lower doped side, in this case the P side. So that gives us the acceptor concentration. That is the N sub B. that we'll use in the next graph. So when we go to the next graph, we're going to take that value that we already had and we're going to put it on the bottom of the graph, and we're going to go and again we're going to intersect with the silicon line, and then we are going to go across, and that gives us our critical electric field. And it's approximately 3.7 times 10 to the 5. Other days it looks like different numbers, but that's what it looks like to me today. So we can use that, and then we can take that information and we can actually find the breakdown voltage and see if it works out. So we go and we check the breakdown voltage. We use the equation we had before, but now we're going to use the doping concentration and the critical electric field. And when we plug in all the numbers for that, we get a value of 110 volts, which is about as good as it's going to get since everything was done with graphs. So that would be certainly anything that would satisfy design characteristics. That would be just fine.